Okay, so yesterday we were discussing about the two cavity klystron. So now this is the equivalent circuit. So at the output cavity, so this C and L represent the energy storage in the cavity. Okay, so GSH is the shunt conductance. So this GH, which will be at the output cavity, represents the shunt conductance, and which accounts for the catcher cavity wall resistance also and beam load resistance also. Okay, and also with the external resistance. So this represents the at the catcher cavity. As I said, this C and L will be the electric and magnetic stored energies. So then we can calculate the cavity resonance frequency, which is given by F naught equal to 1 over 2 pi root LC. Okay, now if I want to calculate the gain, so whatever input voltage which I give at the input cavity, that is puncture cavity, and the output voltage which is taken at the catcher cavity, so the voltage gain which is given by V2 by V1. Okay, so this is the voltage gain for the klystron. So now the mutual conductance, so we can calculate by using this. So the voltage whatever we define at the catcher and the cavity and the buncher cavity, input cavity. Okay, so now from the equivalent circuit we can extract this. So this V2, so you can write the expression for V2, which is given by the B2 I2 by GSH. Now whatever the current which is flowing in the catcher cavity, and also this is a beam coupling coefficient for the cavity, which is a catcher cavity. Okay, and V1 at the input cavity, so we can define it as X, that is a bunching parameter X, and V0 is the beam voltage, and divided by which mode it is happening. Okay, so that N is the number of the mode number. Okay, and beta 1 is the coupling coefficient at the input. Okay, input cavity. So now we can write this V1 so in terms of this. Okay, so now gain we can define in the ratio of V2 by V1, so that will be given by this equation. If you take the ratio, you will get this the gain, voltage gain. Okay, so now for the maximum output power, so we define the bunching parameter X, which is given by 1.841. So that is coming from the Bessel functions. Even J1 of X, for this value you can calculate the Bessel function. Okay, and the GM is the mutual conductance, so which is given by the this equation with respect to the beam coupling coefficient and the conductance, DC beam conductance. So that DC beam conductance we can define it as I naught by V naught. Okay, so this is the calculation for the mutual conductance. So now coming to the applications of this two cavity klystron. So since it is not a low noise device, because it produces, because of the cavity resonances, it slightly it becomes noisy. So therefore it is normally used in the transmitter, not in the receiver, because in the receiver the low noise amplifiers are used. So that's why. So since the two cavity klystrons are a little bit noisy, so we cannot use these amplifiers in the receiver. So instead we can use in the transmitter. Okay, so some typical applications of these two cavity klystrons, so we can use it as troposcatter transmitter in the satellite communication and ground stations, and also in the UHF TV transmitter power amplifier. Okay, so now frequency range where it can be operated is between C band to 60 gigahertz. So C band is 4 to 8 gigahertz. It will start from 4 to the C band is from 4 to 8 gigahertz. So the frequency range from 4 to 60 gigahertz we can able to operate this two cavity klystron amplifier. So now the average power output which is coming from this klystron, or we can achieve, which is 100 kilowatt to 250 kilowatt, and also the power gain is high. So comparatively compared to reflex klystron, which is 30 to 60 dB power gain is possible with the bandwidth of 100 to 60 10 to 60 megahertz, and the efficiency around 30 to 40%. Okay, so this is about the two cavity klystron. So now one of the parameter which is called as beam loading. So in the two cavity klystron, so what is this actually beam loading? So whenever you if you see the structure, so if this drift space which is very small, so when whatever the input whatever input which is the energy of the electron beam which is entering into the cavity, which is same as the energy which is leaving from the cavity. So if this drift space is very small, so now if it is appreciable and the input if it is applied, okay, so because of this RF input cycle, so what will happen, the energy which is entering from the input, so it will not be same, it will be more than that due to this RF energy. Okay, so now when it leaves the maximum energy and it will give the electrons kinetic energy, it will give the energy to the bunching, so that loads the electron beam. So since the RF field which is there here, so that will give the energy to the electron beam, so that the electron beam leaving from the cavity, it is larger than the input, so which is load the beam. So whatever the energy which is already encountered from the RF cycle, it will load the beam. So that's why the energy which is loading to the beam due to this RF cycle, RF positive cycles, so that we'll call it as beam loading. Okay, so that is what the beam loading. So when the buncher cavity is appreciable, the cavity gap, the average energy of electrons leaving the buncher gap is larger than the when they enter the gap, because of the electrons encounter the RF field for a longer duration. So this excess energy will be supplied by the buncher cavity to the electron beam for bunching. So that's why this electron beam loaded by the that is buncher cavity, the phenomenon which is called as beam loading. Okay, and you can use this also as an oscillator to when you give the feedback from the output cavity to the input cavity through some coaxial line. So this can also be used as a oscillator. Okay, so this is what the beam loading, and this is about the application side. So the usage of and frequency range of two cavity klystrons. So now if you do the problem on this two cavity klystron, so a two cavity klystron amplifier is tuned at 3 GHz. So the diff phase length is 2 cm and beam current is 25 milliampere. So the catcher voltage is 0.3 times the beam voltage. So it is assumed that the gap length of the cavity is far less than the diff space, so that the input and output voltages are in phase. So now what we need to compute? We need to compute power output and efficiency for n equal to 5 into 5 1 by 4th so of the time. So since here 1 by 4 is, so as we define the time which is 1 by 4th of the RF cycle period, so that's why it is 5 1 by 4. Don't confuse with the earlier reflex klystron 5 like 3 by 4th of the mode, like 1 by 3 by 4th 2 by 3 by 4th of the mode, which will generate in the reflex klystron. But here we have taken the time transit time which is 1 by 4th of the RF cycle period. Okay, so that's why n equal to 5 into 1 by 4. So now we have to calculate that for this n, and the beam voltage, input voltage and the output voltage for maximum power output for that particular value of n. So now how to calculate this? So use the expressions which is already given, so which I so here I have given the expressions. You can take this expression and you can try to calculate the V naught for two cavity klystron. Okay, so in order to calculate V naught, you have to use this equation. Okay, so that expression is not there. It's just I'll write that expression and try to calculate the beam voltage. Okay, so V naught, which is given by so m by 2 into E, so electron the charge LF, so divided by n square. Okay, so this is the equation for the beam voltage. So now, so m is the mass of the electron, which is given by 9.1 into 10 power minus 31, and 2 into the charge which is given by 1.6 into 10 power minus 19, and L which is given by the length, the drift space length. So how much it is given? So the drift space length is given by 2 centimeter. So and also frequency which is 3 gigahertz, and n is 5 into 1 by 4. So the drift space is 2 into 10 power minus 2, that is 2 centimeter. So convert it to meter. So and the frequency which is given by 3 gigahertz, and the mode is 5 into 1 by 4th of this one, n. So now calculate the what is the beam voltage. Calculate what is the beam voltage. Hello, anybody calculated?
1.65 microvolts.
Microvolts. This is
Yes,
square,
sir.
no? This is square. So here it is square, so you need to do the square of this.
Three point seven into 10 power minus 8.
10 power minus 8, is it? Check it once. So what is this? If you do this one square, so 3 into 3, 3 to the 6, 6 into 6, 36 around. So into 10 power minus 4 into 10 power 18. Okay, so this divided by 5.25 square. So this will give, so this parameter I am writing.
So 64.51 into 10 square.
Anybody got other answer? So generally
So 64.51 into 10 power 2.
64.51
51 into 10 power 2.
10 power 2. So this parameter or whole answer?
So whole V naught.
Okay, so that means it is around 6,000 something.
Yes, sir.
Now check it once, calculation properly, because generally the beam voltage in terms of 200s or 300s.
371.
How much?
371.42.
Okay, so 371 it may be the correct, because the beam voltage, so this will be in terms of the 200 to 400 range. So always you make sure that the beam voltage it is falls within this range. Okay, so now this may be the correct answer, so you can take this answer. Okay, so now for the maximum power output, so we need to calculate what is the maximum power output. For that, bunching parameter we already know, that is 1.84, that is predefined. Okay, and you know the that bunching parameter equation, which is given by pi n v1 by v0. Okay, so now if you do this one, so we can calculate what is v0, because we know v0, and we can calculate v1. So for n, so we know n 5 of 1 by 4th. Okay, so now calculate what is v1. So now v1 which is given by x v0 divided by pi into n. So what is the value of v1? So what is the value of V1? Because V1 is, so this is the expression for bunching parameter, which is equal to pi n V1 by V0. So now V1 equal to x V0 by pi into n. Okay. So now what is the value V0? Chandana, are you calculating? Hello.
Yes, sir.
What is
Yes,
the
sir.
value of V1?
Sir, I'm calculating, sir.
So now tell me the value of V1. So which may comes around 41.4 volts. Check it. So this is the value of V1. So now we need to calculate what is, that is V2, the catcher voltage. So V2, so which is given by here, so the 0.3 times of the beam voltage. So it is already given in the problem, the catcher voltage is 0.3 times of the beam voltage. So now we know beam voltage V0, so which is 0.3 times into V0, which is equal to 0.3 into what is V0? V0 is, we have calculated, which is around 371.2. So you calculate, so which is 0.3 times means 100, around 100 it is coming. So 111 point something it will come. So calculate it and tell me, or we can write it as 37.12 divided by 3, so which is equal to, sorry,
It's 111.36.
how much?
111.36.
Okay. So the value which is given by 111.36 volts. Okay, this is V2. Okay, so now we need to calculate the output power, which is P0, which is given by the 0.582, so I0 into V2. So this is the output power maximum expression. So take this and the beam current which is given. So what is I0? 25 milliamperes. So substitute and you will get the V2 into I0 and you will get the maximum power output. How much it is maximum power output? So which is 0.58 into 25 milliampere into 111.36. How much is the power output? How much watt?
1.61.
Okay, 1.61 watts. So this is a maximum power output we will get. So now what is the efficiency? Efficiency will get it as, so 0.582 into V2 by V0. So this is the equation. Or you can calculate even the RF power by DC power. So that also you can do. So this is another expression for efficiency. So which is given by the V2 by V0. So now we know V2. So what is the value of V2, which is 11.36 divided by V0, which is 371.2 into 0.582. So how much the efficiency?
17.46%.
Okay, 17.46%. So this is the efficiency of the two cavity klystron for this particular problem. Okay. So now take this one. another one, an identical two cavity klystron amplifier operates at 4 gigahertz with V naught equal to 1 kilowatt, I naught equal to 22 milliampere. So cavity gap 1 mm, drift space is 3 centimeter, and if the DC conductance and catcher cavity total equivalent conductance are so this much, 0.25 into 10 power minus mhos and 0.3 into 10 power minus 4 mhos. So now what we need to calculate, beam coupling coefficient, DC transit angle in drift space, and input cavity voltage V1 magnitude for maximum output voltage, and what is the voltage gain and efficiency. So efficiency neglecting the beam loading. Okay, so now for this, first we need to calculate the what is drift velocity, that is u naught. Okay, so we need to calculate what is the drift velocity u naught first. So then by using drift velocity we can calculate what is the transit angle, which is theta naught, so which is given by omega d by u naught. Okay, so omega you can calculate, so from the frequency. So now first we need to calculate what is the drift velocity, so that is DC beam velocity u naught, so that is u naught equal to 0.593 so into 10 power 6 into root v naught. So that we can use this equation which is given here, the DC beam velocity. Okay, so 2e v naught by m, so that will give 5.93 to 10 power 5 into root v naught. So the same equation which I used here. Okay, so or 5.93 into 10 power 5 into root v naught, or 0.593 into 10 power 6 into root v naught. So now v naught it is given 1 kilo volt. So what is the u naught? Calculate what is u naught. So substitute 1 kilovolt here, 10 root of 10 power 3, and you will get the value. What is the value?
18.75 into 10 power 6.
18.75 into 10 power 6. Okay, so this is the DC beam velocity. So now calculate, so the theta naught, so 2 pi into 4 gigahertz into the drift this one, the space which is 3 centimeter. So substitute and you will get, sorry, this is the cavity gap. So the D is cavity gap because here the D is mentioned as cavity gap. Yeah, so this D is mentioned as cavity gap, which is given by 1 millimeter. So now substitute this one, 1 into 10 power minus 3, omega is 2 pi into 4 gigahertz, so divided by u naught, whatever you are getting. So now calculate what is theta naught. So calculate what is theta naught, which is equal to omega d by v u naught, that is DC beam velocity. This is 2 pi into 10 power 4 into 10 power 4, sorry 10 power 9, 4 gigahertz into 1 into 10 power minus 3, 1 mm, so divided by 18 point, so how much we got DC beam velocity, 18.75 into 10 power 6. So now what is theta naught? So whatever you are getting, this is in terms of radians. Okay, you need to convert if it is required to the degree. Okay, so how much it is coming, theta naught?
0.34.
1.34, sir.
Okay, 1.34 radians. So now we need to convert this one into degree. So how we will convert? Multiply by how much? So pi means 180 degree, right? So you can, if you want in terms of 1 degree, you have to pi by 180, you multiply and you will get the, so the in terms of degrees. So this is how much, 1.34 radians we need in terms of degree. You can put it as x. And what is x? X equal to 1.34 into 180 by pi. So how much it is coming in terms of degree?
.77 degree.
Okay, so this is in terms of angle. So that is the gap transit angle. So this is the gap transit angle, whatever which is given to calculate. Okay, so now we need to calculate beam coupling coefficient for the both the cavities, that is beta 1 which is equal to beta 2, and which is equal to in the form of sin theta naught by 2 by theta naught. This is sin x by x formula. And so in order to calculate this one, so you take it in terms of angle, and this one you take it in terms of radians. Okay, in order to calculate beam coupling coefficient, so this is nothing but sine of, so 76.77 by 2, so this divided by 1.34 divided by 2. So now what is the beam coupling coefficient? Or you can put it in terms of radians in the calculator, and you can calculate the sine of that value. So both it will give same. Since it is always in terms of degree, so you can put it in terms of degree. So what is the value?
.84 into 10 power minus 6.
Sir, if we do it in degrees, it is coming 0.926, sir.
Okay, yeah, that's what. So we have already converted this one into degree now. So how much it is coming?
0.96.
0.92. So that is fine. Okay, 0.92. So this is a beam coupling coefficient. So because we have converted, so this radians into degrees, you can put it in degree mode and you can calculate. Okay, so this will be 0.92. So now we need to calculate what is the DC transit angle in the diff phase. So that is given by some theta 1. We can represent theta 1. So which is nothing but omega L divided by, so u naught. So this L is the space, so which is given. So you can put it 3 centimeter, and omega you know 2 pi into 10 power, that is 4 into 10 power 9 the frequency, and L is the space which is given by 3 centimeter. Is it 3 centimeter here? So put it that, and you already know the beam velocity. So DC beam velocity which is given by 8.75 into 10 power, so how much we got? 10 power 6. So that you put and you calculate what is this. So this is, so or you can put this one as gap transit angle theta g. Okay, and this we can call it as theta naught. So that is DC transit angle.
So 4.0192.
4 point,
0192.
okay, radians. Okay, so this is in terms of radians. So just calculate it in, once again, is it correct? So somewhere the power set is missing. So it's around 40, which I got the answer, which is 40.
40.212.
Yeah, 40.21. So it is around 40.2. It is 40.21. Okay, so now this is the DC transit angle. So now we know for the maximum power output, the bunching parameter should be x equal to 1.84. So now if you calculate the Bessel function, so you have the Bessel function sheet, so which we can calculate for the particular value of x. So now for this particular value of x, the Bessel function gives the value 0.582. so in the problem this will be given, so don't worry about that. The bunching parameter and Bessel function parameter, it will be specified. Okay, so now for this value, so the input cavity voltage we need to calculate. So for that, so expression is 2 v naught into x divided by beta 1 into theta naught. So now we calculated the beam coupling coefficient and the DC transit angle. We know the beam voltage and bunching parameter. Calculate the value of v1. Okay, the input voltage, so which is we need to calculate input cavity voltage for maximum output voltage. So where the maximum output voltage uh, will be the maximum voltage output when x is this value. So put this value and calculate the input voltage. What is that? 2 into, so v naught how much, which is given 1 kilovolt, right? Yeah, so v naught 1 kilovolt, 1 into 10 power 3 into 1.84 divided by beta 1, that is coupling coefficient, which is got 0.92 into theta naught, which is 40.21. So how much the v1?
$91.47.
91.47 volts. Okay, okay, around that only.
99.
Okay, so now we need to calculate the what is the voltage gain and efficiency. So we know the equation for voltage gain, which is given by the v2 by v1, so the output voltage by input voltage. Okay, so that we have just now we have seen, right? So here, so v2 by v1. So or you can use this equation because we know the parameter beam coupling coefficient, DC transit angle and all these things. So we can use this AV equation, that is voltage gain equation also. Okay, so if you use that, so you will get that, or if you know v2 and v1, you can directly calculate it. Okay, so since v2 is doesn't know, so you can use the AV, which is equal to beta square theta naught into j1 of x into I naught divided by x v naught into GSH. So now G, the shunt conductance, it is given. V naught we know, the bunching parameter we know, and the Bessel function we know. So I naught it is given. So I naught value, which is given in the problem. So 22 milliampere. So substitute that, and the GSH, the shunt conductance, which is given, how much it is given, point so the total equivalent conductance and DC beam conductance which is given. So now we need to calculate the GSH. Okay, okay, that shunt conductance, which is here, can calculate using this equation, or you can okay, so the GSH which we need to calculate here, so that it will be the using these two conductance, that is catcher cavity total equivalent conductance and the DC beam conductance, so G naught. So this is the addition of these two, so the DC beam conductance and also the cavity total equivalence conductance, so that you will get the GSH. Okay, so GSH, you can add these two to get it. Okay, so if you add these two, 0.25 plus 0.3, which is given by 0.55 into 10 power minus 4, that you can take it as GSH. Okay, so GSH, which is given by, so G naught plus that DC beam conductance and also the the catcher voltage, that equivalent conductance, or you can call it as GE, so which is given by, this is, so what is DC beam conductance, so which is given by the 0.25 into 10 power minus 4 plus this one total equivalent conductance, which is given by this one. So now GSH, which is given by 0.55 into 10 power minus 4. So now put this value here. Okay, and you know all the parameters, the beam coupling coefficient, which is calculated, and theta naught. So now you can calculate what is AV. Okay, so now AV is given by 0.92 square into theta naught. How much theta naught in terms of radians? So which is 40 point something 12. So into J1 of x, which is given by 0.582, and I naught, which is given by 22 milliampere. Okay, so this divided by x is 1.84. so V naught, which we have V naught, which is given 1 kilovolt, so that is 10 power 3 1 kilovolt, and the DC, that shunt conductance, that is 0.55 into 10 power minus 4. So now calculate what is AV. What is the value of AV? Hello? So 4.38. Okay, so so the value AV, it is 4.38. Okay, it is correct. So now we need to calculate what is V2, so which is given by AV into V1. Okay, so from this equation, so we need to calculate what is V2. So calculate it, so which is given by 4.38 into, so what is V1? V1, which we got, so 91.47. Okay, so this is V2. So calculate it, how much? How much is the output voltage V2?
Four 400.638.
Okay, 400.63. Okay, so this is the V2 voltage, and the power efficiency, which is given by the equation. So the power efficiency you can calculate, so that is the RF power divided by DC power. Okay, so that you can use this equation, which is also given by beta square I naught J1 of x V2, so this divided by I naught into V naught. So I naught V naught, this is DC beam voltage and DC beam current. So this will be, so cancel each other and we can calculate beta square J1 of X V2 divided by V naught. Okay, so this is given by 0.92 square into 0.58 into V2, which we calculated now, that is 400 point, so something 400.6 divided by the V naught, that is 1 kilowatt. Okay, so what is the efficiency we got?
$19.66, sir.
19.66 percentage. Okay, so this is the efficiency which you got. Okay, so this is about the efficiency. Okay, so this is about the problems on the two cavity klystron. So use the appropriate expression, so you can refer these equations, so which have included in the problem, new one, so that I will include and I will update the PPT and I will send you. Okay, so now one more problem is there, so that we will do in the next class, or you can take this problem and try to do your own. Okay, so in a two cavity klystron operates at 10 gigahertz with I naught 3.6 milliampere, V naught equal to 10 kilo ohm, the drip space length 2 centimeter, output cavity total conductance is GSH, which is given 20 micromho, and DC beam coupling coefficient 0.92. Find the maximum voltage and power gain. So now we can calculate what is the V2 and the power gain. So we can directly calculate what is V2, so which we use earlier problem, so the same equations we can use. So AV, first you calculate AV and V naught, which is given, and you can calculate what is V1. So maximum voltage gain, how you will calculate? So you calculate first the voltage gain AV. Okay, and then so calculate what is DC beam velocity, then you can calculate transit angle. So later, so you will get the what is the